On the 17th of January 1803, a 26-year-old man called George Forster was hanged in London after being convicted of murder. Within a couple of hours, his body was laying on a table at the Royal College of Surgeons. Standing over him was an Italian physician called Giovanni Aldini, holding some metallic instruments in his hands, which were wired up to some strange troughs nearby. Aldini was investigating an amazing new chemical discovery called Galvanism, named after his uncle, Luigi Galvani, who had first discovered it. Aldini leaned over and prepared to touch the instruments to the dead man's face, and, in his own words, on the first application of the arcs, the jaw began to quiver, the adjoining muscles were horribly contorted, and the left eye actually opened. Whatever strange chemistry was going on in those troughs was having an effect that horrified the other people in the room. To them, it seemed as if Aldini was bringing the dead back to life. News of this amazing demonstration quickly spread around London, and eventually caught the attention of a young Mary Shelley, who, a few years later, at the age of 20, used it as inspiration to write what would become one of the most famous novels in English literature, Frankenstein. In this video, I'll be covering one of the most incredible discoveries in the history of science. This is the story of electrochemistry. The concept of electrical charge goes back a long way. The Greek philosopher Thales of Miletus, who lived around 600 BC, wrote about how if you rubbed a piece of amber, it would start attracting things like hair or feathers towards it. He believed that applying friction to it turned the amber magnetic, in contrast to the naturally occurring mineral lodestone, which was permanently magnetic without any friction. This strange property of amber was certainly interesting, but for the next 2,000 years, nobody investigated further. That was until the year 1600, when the English physician, William Gilbert, personal physician to Queen Elizabeth I, published a book called De Magnete, where he outlined his research into the strange attractive forces due to amber and lodestone. And he confirmed that they were indeed two different forces, as they were produced differently and they attracted different things. In this book, he gave a name to the force produced by rubbing amber, and named it after the Greek word for amber, electron, giving him the adjective electricus, and hence the anglicized version, electric. Over the next century or so, various scientists investigated what we today would call static electricity, including an American founding father, Benjamin Franklin, who was one of several scientists of the time who invented a machine that can build up an electrostatic charge to be discharged later on. Having a pretty good idea of what an electrical discharge felt like, he went on to perform his most famous experiment, where he hung a key from the string of a conductive kite and flew it in a thunderstorm to demonstrate that lightning, which wasn't very well understood at the time, was indeed an electrical phenomenon. Franklin also introduced some electrical terminology that we still use today, positive and negative. He thought that an electrical current is due to the flow of some kind of electrical fluid, and that it would travel from a material that contains an excess of this fluid, which he termed positive, to a material that is lacking in the fluid, which he termed negative. Exactly what this fluid was, nobody could say. So, by the late 1700s, scientists knew a thing or two about static electricity. It was around this time that the Italian scientist Luigi Galvani began investigating the effects of static electricity on animals, specifically frogs' legs. Using a static electricity machine, one of his assistants started prodding around the frog's legs to see what would happen. At one point, he touched one metallic conductor to a nerve and the other to a muscle, and the muscle contracted. This would have been extremely shocking, if you'll pardon the pun, to witness. Galvani knew that something amazing had been discovered here, so he got to work investigating it further. One of the most interesting observations he made was that the strength of the muscle contractions didn't scale linearly with the strength of the spark. Sometimes he was able to get a large contraction with barely any spark at all. Because of this, Galvani wondered what would happen if he removed the static electricity machine entirely. So, he touched the metal contacts to the nerve and to the muscle, then touched the contacts to each other to complete the circuit, and the muscle contracted. This was a huge breakthrough. It turns out that you didn't need the spark at all. To Galvani, it seemed as if the nerves contained their own internal electricity, which could be conducted using the metal contacts to the muscles to make them move. Galvani called this animal electricity, and he believed that it was evidence of a vital force which gave life to organic matter. By the way, just a quick one, this video required a lot of research. At one point I had around 30 tabs open at once, which would have been extremely confusing except for the fact that I was using Opera as my browser, which has a load of cool features that are really helpful if you do a lot of research like I do. For one, it lets me group my tabs into collapsible tab islands, and you can see here that I've made separate islands for the different scientists I was researching. I can name different tab islands and even choose different colors. It saves space and helps me organize my workspace. Also, you know that annoying moment when you click away from one tab and then have to spend ages trying to find it again? Opera has a solution to that with tab traces, underscores on your most recently viewed tabs that appear darker the more recently you were on that page, making it a breeze to navigate your way at a glance. You can also drag up to 4 pages to create a split screen view with different possible layouts. I found this to be really helpful when jumping between the different pages of old lab notebooks that I found online. Finally, Opera AI allows you to analyze your current tab or an entire tab island. It's now even faster and smarter than it was before. It's completely free and it doesn't require an account. Remember, it's important for any scholar to thoroughly double check this information, but I've actually found it to be a really great jumping off point for research. For instance, I found an online copy of Galvani's original 1791 book written in Latin, and the AI was able to give me a really helpful summary. To try it out for yourself, for free, check out Opera using my link in the description. Okay, back to the video. Soon after Galvani published his book on animal electricity, another Italian scientist called Alessandro Volta got to work recreating the experiments, but Volta quickly came to a different conclusion. According to Volta, Galvani had everything backwards. The contractions weren't due to animal electricity contained within the nerves flowing through the metal conductors to the muscles. Instead, the electricity was coming from the contact between the metals themselves, which then transferred to the muscles, causing a contraction. In other words, Volta believed that the frog's legs had nothing to do with the electricity at all. They were just receiving the current that was being generated by the 2 pieces of metal in contact with each other. Volta set out to prove this by creating a similar setup with no frog's legs at all. To demonstrate how it worked, I bought myself some copper and zinc discs, the same metals that Volta used. He took one of each and stacked them on top of each other. To separate them, rather than using frog's legs, Volta used a piece of cardboard or cloth which was soaked in brine. By completing the circuit, he observed that he was able to get a current. When I did this, I managed to get a voltage of around 0.6 volts. Volts, by the way, are named after Volta, in case that wasn't obvious. Volta wondered if adding more layers would increase the current. So that's exactly what he did, separating each pair of discs with a piece of brine-soaked cardboard, and he observed an increase in current, just as he'd predicted. When I tried to replicate this, I found that my voltage actually decreased. It then took me an embarrassingly long time to figure out what I was doing wrong, but eventually I realized that I had placed a cardboard piece between every single disc, completely overlooking that the whole point is to have contact between the 2 metals. Don't judge me, it was late and I'd already worked a full day of work, okay? But once I fixed this by removing every other cardboard disc, so that the sequence now went copper, cardboard, zinc, I was able to get a voltage of around 4 volts, enough to light this little LED. This pile of discs became known as the Voltaic Pile, and it was the very first electrical battery. Unlike the static electricity machines that require the user to build up the charge with friction to then be discharged all in one go, the Voltaic Pile was able to provide a continuous, stable current. It was also able to cause muscular contractions in animals. Despite Volta disproving Galvani's theory of animal electricity, he chose to honor Galvani when he named his process for generating a current, calling it Galvanism. Galvanism can also be demonstrated by sticking a strip of zinc and a strip of copper into a lemon. You may have done this at school at some point. Here, the lemon juice acts as a substitute for the brine-soaked cardboard, or the frog's legs, by conducting the current between the pieces of metal. One single lemon cell gave me just under a volt. Connecting 4 in series gave me just under 4 volts, again enough to light an LED. By cutting them in half and connecting 8 lemon cells in series, I produced over 7 volts, almost double what I got from my Voltaic Pile. So either my lemon battery was really good or my Voltaic Pile was really bad. Volta became internationally famous for his Voltaic Pile. Here's a painting of him demonstrating it to Napoleon. However, there was a problem with the Voltaic Pile. The heavy metallic discs would compress the brine-soaked cardboard, causing the brine to leak out, which resulted in a short circuit. This problem was quickly solved by a Scottish chemist called William Cruickshank, who noticed that the problem was greatly reduced when he laid the metals horizontally. This led him to invent an improved form of the Voltaic Pile, which became known as the trough battery. Here, a wooden box was lined with an insulating resin with zinc and copper plates securely welded in at an even spacing. Instead of brine, he poured dilute sulfuric acid between the plates and found that it worked much more reliably than the Voltaic Pile. This leads us on to Galvani's nephew, Giovanni Aldini, from the start of the video. Using 3 trough batteries connected in series and, to the horror of the observers in the room, he was able to make George Forster's body move, inspiring Mary Shelley to write Frankenstein, which she published in 1818. Now, let me give you this fun but gruesome fact. In these early days of electrochemical experimentation, scientists needed a way to make sure that electricity was flowing in their circuits. Devices for quantifying current wouldn't be invented for a couple of decades, so they used something more crude. The English scientist Michael Faraday, who went on to be known as a major contributor to the fields of electrochemistry and electromagnetism, had a laboratory in the Royal Institution. This laboratory has been perfectly preserved at the Royal Institution and it's completely open to the public, so I strongly recommend checking it out if you're ever in London. I myself went around 3 years ago when I was researching my first ever video on the history of chemistry, all about the history of benzene, and I saw this. This is the original lid to Faraday's froggery. It would have topped a box that was filled with live frogs. Whenever Faraday needed to check if electricity was flowing, he would open the box, grab a frog, and smash its head in with a hammer. Then, following in Galvani's footsteps, he would connect electrodes to the legs, and if they twitched, he was good to go. Luckily for the frogs, Faraday later invented a device he called a voltameter, which replaced the froggery entirely. The invention of the Voltaic Pile quickly changed the world of chemistry. In 1801, a young English chemist called Humphry Davy gave his first series of lectures to the Royal Institution and chose to speak about the exciting new field of galvanism. If you've watched my videos before and you recognize Davy's name, he's the one who had spent the previous couple of years huffing nitrous oxide and meticulously documenting his experiences. Don't get me wrong, he was a phenomenal chemist and a brilliant thinker, but that didn't stop him enjoying the odd laughing gas party here and there too. I'll link my video about that story in the description below, it gets pretty wild. But now we pick up where that video left off. Davy, still in his early 20s, had moved from Bristol to London and gotten hired at the Royal Institution as an assistant lecturer in chemistry. Very quickly, his lectures became extremely popular. People travelled from all over to witness this passionate young chemist perform all kinds of amazing experiments in front of them. In fact, Davy's lectures became so popular that Albemarle Street, where the Royal Institution is located, would get completely blocked up with horse-drawn carriages whenever one of his lectures was on, so as a result, Albemarle Street became the first one-way street in London, just to handle the traffic. When he wasn't lecturing, Davy was in the lab and, moving on from his research on nitrous oxide, began researching the exciting new field of galvanism. You see, going back a bit to May of 1800, just weeks after Volta had announced his work, 2 English scientists working at the Royal Institution, William Nicholson and Anthony Carlisle, used a voltaic pile to pass a current through water, and they found that the water around each electrode started bubbling. When they trapped the gases being given off, they found that the gas being produced at the negative electrode was hydrogen, and the gas being produced at the positive electrode was oxygen. They realized that they had actually split water into the 2 elements that make it up. This process was called electrolysis, and it inspired Davy, who wanted to see if he could use it with any other substances. Over the next few years, much more powerful batteries were developed, which allowed Davy to do some really cool experiments, and in 1807, Davy performed his greatest experiment so far. On the 19th of October, he took a bell-shaped container with a platinum wire fused through the top. We can see his sketch of it here in his original lab book. Inside, he placed some damp potash, a caustic substance extracted from wood ash that had been used for centuries in chemical processes such as soap making and gunpowder production. To seal it off, he placed the open end of the container over a bed of mercury and fed another wire in through the bottom. He then connected the top wire to the negative pole of a massive battery and the bottom wire to the positive pole, and in his words, observed that the mercury became oxidated. He also observed small metallic globules appearing around the platinum wire at the top, which actually caught fire. When he swapped the poles of the battery around, he observed that gas was developed in great quantities from what was now the positive wire. Underneath, he wrote, "This gas proved to be pure oxygen. proving the decomposition of potash. So, from a modern chemistry perspective, Davy had managed to separate the oxygen from this mystery metallic element, which together formed potash. Davy's cousin, Edmund Davy, who was assisting him at the time, later wrote that when Humphry saw these metallic globules form, he actually danced about the room in ecstatic delight. Later in the same day, Davy casually noted down the discovery of another element from another source when he wrote, "Soda decomposed with different phenomena," although he didn't give any details here as to what those phenomena were. So in just one day, Davy had isolated two brand new elements, one from potash and one from soda ash. Soda ash was similar to potash, except it was extracted from a different type of ash. Both could also be mined in various places, so there was plenty of it around, and now Davy had just unlocked their compositions. Davy named the element from potash potassium, and the element from soda ash sodium. They were both highly reactive metals which could be cut with a knife and would quickly oxidize when left in the air, but could be stored for longer under oil. When dropped into water, they both reacted violently. When demonstrating these new elements to his enraptured audiences, Davy actually built a miniature volcano, placed some potassium in the top, sprayed water in from a safe distance, and the spectators gasped and cheered as his volcano erupted into flames. Within 2 years, Davy had used the same electrolytic process to isolate 5 more elements: barium, calcium, strontium, magnesium, and boron. He became internationally renowned for his work and was knighted in 1812. To this day, he's rightfully regarded as one of the greatest chemists of all time. So we've gone from a scientist in Italy prodding frogs' legs and wondering why they're twitching, to just a few years later when a chemist in England had used the exact same principle to isolate 7 new elements. How incredible is that? It just goes to show you the amazing things that can happen when you're curious enough to keep asking questions. Guys, just a very quick reminder that you still have a couple of days to head over to chemistorian.dashery.com to take advantage of my launch sale. Check out official Chemistorian merch, including this really cool Radium t-shirt. It took a lot of back and forth between me and the designer to get something I was happy with, but just look at how cool this is. I wanted to have a grungy rock and roll band t-shirt with a Chemistorian twist, and I'm really happy with how it turned out. I also made a design myself. This one is for you science nerds out there. It's inspired by my History of the Atom video, and it shows the evolution of the atom, starting with Dalton's solid sphere model, then Thomson's plum pudding model, Rutherford's nuclear model, Bohr's quantum shell model, and finally Schrödinger's electron cloud model. Both of these designs are available on all kinds of merch, including t-shirts, hoodies, mugs, wall art, and more. So if you've been looking for a way to support the channel, now's the perfect time to get yourself some Chemistorian gear. I hope you enjoyed the video, and if you made it this far, please consider liking and subscribing. It really helps to tell the algorithm that this video is worth watching. Also, if you'd like to support further, check out my Patreon for bonus content. Thanks for watching, and I'll see you in the next one.